So we're starting. So today we'll be talking about backtracking and branch and bound. Last time, in the last 10 minutes of last lecture, we gave an introduction to this by showing a representation of a brute force algorithm for solving the 0-1 knapsack problem. And last time we drew this tree, which we called decision tree, that decides what to do with each item. For example, at the first level, in the tree we decide what to do with item 1. So this is item 1. Take it or not take it. If we don't take it, then we'll have to decide what to do with items 2 and 3. And if we take it, we will also have to decide what to do with items 2 and 3. Then for item 2, we have to do the same thing. With item 3, we have to do the same thing. So this solution, each leaf in this tree is going to give us a solution, one of the solutions. Each leaf is a complete solution. Each internal node in the tree represents a partial solution. So there are partial solutions and complete solutions. Each leaf is a complete solution. So for example, this solution deciding not to take any of the items will give us the empty set. This solution, item 1 don't take, item 2 don't take, item 3 take, so we will end up with item 3. This solution, for example, take item 1, don't take item 2, take item 3, we will end up with 1 and 3. So in this case, 0 is don't take, and 1 is take. And in a brute force solution, we examine every solution. And as we said last time, for the 0-1 knapsack, we'll have 2 power 9 solutions. So the number of leaves here corresponds to the number of solutions, the total number of solutions, all possible solutions. There are 2 power n of them. For n equals 3, we have 2 power 3, which is 8. We have 8 leaves in this case. For each solution, we're going first to check if it's feasible or infeasible. And for the 0-1 knapsack problem, feasible means what? Fits in the capacity. Yeah, fits within the capacity. Or sum of weights, or sum of taken weights is less than or equal to the capacity. Sum of taken weights, or more precisely, sum of weights of taken items is less than or equal to the capacity C. And in this case, a couple of solutions are infeasible. One of them is this solution that takes all items. Obviously, all items are not going to fit, so the sum of weights of all items is what? 6 and 5, 15, and the capacity is 12, so this is infeasible. Which other solution is infeasible?
The last one first.
Well, 2 and 5 is feasible. 5 and 9 is infeasible. So 5 and 9 is 2 and 3. So this one is infeasible. For the other solutions, we can write the value of each solution. So this solution is going to give us a value of 0. This solution is going to give us a value of 30. This is going to give us a value of 20. We don't care. This is infeasible. 10. 1 and 3, 40. 1 and 2, 30. And we don't care about this. And in fact, in a brute force, we will be traversing this tree in some order. Usually the easiest order for traversing the tree is going to be depth first order, because if you do recursion, and we will see towards the end of this lecture that the straightforward way of implementing this or generating this tree is to use recursion. So you make a decision then you do the same thing. You keep repeating at each node. So it's the recursive nature of this can be seen by realizing that what we are doing here is that we are making a decision, then we are basically starting over. Now it's like this becomes our new route. So we do the same thing, make a decision, and now this is the new route. Make a decision, and this is the new route, and so forth, until we get to a leaf, after we decide all the items. This will become clearer when we write the actual code. So we will write the pseudocode towards the end of this lecture. But for now, we will be going through these solutions, and we will keep track of the best solution found so far. So if we go through this in depth first order, we will find this solution first. So now our best solution is 0. Then we will find this solution, and this has a value of 30. So now our best value is 30. After we discover the 30, now we are going to continue to traverse the tree. So we're going to go back to this node, then to this node. Then we will make the decision. We will change the decision from not taking item 2 to taking item 2, and we will go along this path, and we will get to this solution. And this solution will say item 2 and will give us a value of 20. So we keep track of the best solution found so far. So at this point, this is not better than the best solution. The best solution so far is this. So our best solution so far is 30. So this does not update the best solution. And when we get to this, we realize it's infeasible. So we skip it. This is 10, does not update the best solution. This is 40. It updates the best solution found so far. So this is going to be the best solution so far. Then when we visit this solution, it does not update the best, and this is infeasible. So after going through all solutions, we keep track of the best, and in this case, this is the best, which is the optimal solution. So this is brute force. It's, conceptually, this is easy, right? It's just you enumerate all solutions. But in terms of efficiency, this is exponential. And in the early lectures, we did the math, and we saw that exponential does not complete within reasonable time, and the time grows exponentially, right? So if you have, 2 power 20, 2 power 20 is approximately equal to 10 power 6 operations. So this is doable. So this is going to be done in a fraction of a second. But if you go to 2 power 30, this is 10 power 9. So this is a billion operations. So now, considering that you will be running this on a gigahertz processor with 2 or 3 gigahertz clock speed. So this is likely to take seconds, because each operation is going to take on average many cycles, maybe 10 cycles, tens of cycles on average. So this is going to take a few seconds probably. Now when you go to 2 power 40, how much more time will it take? The point here is that when you go from 230 to 240, 2 power 40 equals 2 power 10 multiplies by 230. And 2 power 10 is 1,000, roughly, 1,024 exactly. So this means that by increasing the input by 10, the number of operations gets multiplied by 1,000. And so the number of operations is gonna explode exponentially, right? So by the way, you'll be doing this in assignment 4. So in assignment 4, giving you these numbers so that you know what to expect. So when you run 2 power 30, you expect this to complete within seconds. But when you go to 2 power 40, that's thousands of seconds. Okay, so now thousands of seconds, that's in the hour range. And then when you go to 2 power 50, that's millions of seconds. So you'll be doing this in the assignment, and you will be doing brute force. Then you'll be doing the backtracking and the branch and bound that we will be studying, and you will see how much difference that can make. Well, so this is brute force. Now what's backtracking? Backtracking means you don't do brute force. You just observe that you don't always have to go all the way to a leaf node. Sometimes you can discover early that you will not find a solution and that you are already infeasible. For example, here if we change the capacity, say to 6, if the capacity equals 6, now when you are here, you take item 1, now you have a weight of 2. You take item 2, now you have a weight of 7. You track the weight that you have taken. So if you take items 1 and 2, your taken weight is 7, and your capacity is 6, which means that you are already infeasible, and there is no point in continuing any further. So this is not clear on a small example like this, but if you have a bigger example with, say, 50 items, you have 50 items, and after deciding what to do with the first 20 items, you fill the knapsack with the first 20 items. They fill the knapsack. Then there is no point in considering the remaining 30 items. So the power of this is not clear on a small example like this. But if we consider a bigger example with 50 items, of course, I'm not going to draw a complete 50-item example. So we'll say, OK, here at this node, we have decided 20 items. 20 items have been decided. 30 items are yet to be decided. Now, decided means we decided take or not take. The ones that are yet to be decided, we haven't decided yet. But if the sum of weights of sum of, let's call it sum of taken weights, is greater than C, is already infeasible, there is no point in wasting the time to decide what to do with these remaining items. So in this case, this whole subtree below this node is not interesting and can be pruned away. So you can prune it. You can prune the whole subtree. Prune the subtree below a node that is already infeasible. A node that is already infeasible. So this is basically what backtracking is. You try to, and of course, by backtracking we mean we just don't go any further and we backtrack. We undo the last decision. So the last decision may have been, take item number 20. So we undo this and we consider the other option, which could be, well, assuming that we did, take before untake, then untake is going to be here. You will have, well, I'll have to do it here, but it doesn't make sense. Well, let's assume that we are traversing the tree from right to left. So you get the idea. The idea is that we tried taking item 1, and now we'll backtrack and try not to take item 1. And maybe now by not taking item 1, we will get a sum of weights that is within the capacity. So this is going to be feasible, and we can continue further. Okay. So the idea is you try to determine as early as possible whether a given node is feasible or not. And if it's infeasible, you don't go any further. You backtrack, and you consider other decisions. Okay. So here, just to make it clear, so what we'll be doing is this. 0. So you backtrack to this and you consider this, which is 0. And even if with the 0 it's still infeasible, you just prune this and you go to this node and then you undo another decision and so forth. So you go back in the tree. So because you will be backtracking to consider other decisions. Okay. So this is backtracking. So you will be implementing this in assignment number 4, and you will see that this will give you that can make a difference. This simple idea can make a measurable difference in terms of time. So you will be doing the timing for brute force and the timing for this backtracking. Only backtrack when you exceed the capacity of the knapsack, and you will see that there will be a measurable difference in time when you do this. Okay, but now this is not the best that we can do. We can do much better than this. We can do branch and bound. So what does branch and bound mean? Branch and bound means is if you get to a certain point, to a certain node in the tree, and let's draw a better tree. You are at this node here. So this is the root, and you got somehow to this node. And the sum of taken values equals 50, say. And your best solution so far, best solution is 100. If your best solution is 100, and the sum of taken values at this point is 50, and the sum of undecided or sum of values of undecided items equals 40. The question is there a point in going any further? Yes or no? And why not?
No.
Okay, no, why not?
Because the total, the maximum we can obtain is 90.
Yeah, exactly. So the idea is, with the decided items, we already have a value of 50. With the undecided items, the items that are yet to be decided, the total sum of their values is 40. So this means that even if we take all of them, we're going to get 90. But the best solution is already 100. So even if we take all the remaining items, we're not going to be able to beat the best solution found so far. So this 90 here is an upper bound. 90 here is an upper bound. Now it's an upper bound in the sense that, we did not say that there exists a solution that, in which we will be taking all the undecided items. We don't care. We are not saying that such a solution exists. It may not exist. But any solution that will exist is going to be, will have at most a value of 40, if not less. Okay, so we don't care. Anything that is less than 40 will still be less than the best, and we don't care. So what this means is that if we got to a node with this situation, every leaf below this node is not going to be interesting. So the leaves will have values, and we know that none of these will have a value that is greater than 90. So we may have a 90 here, 80, 85, 87, 60, whatever. But we know that nothing will exceed 90. That's why 90 is an upper bound. So this is exactly the idea of branch and bound. So bound means try to compute a bound. Well, if you are doing a maximization problem, try to compute an upper bound. This is a maximization problem. We are interested in an upper bound. An upper bound on the value of any solution in the subtree below a given node. And if you can compute an upper bound, and this upper bound is less than or equal to the value of the best solution found so far, then there is no point in continuing any further. And you can prune this subtree. You can prune the entire subtree and backtrack. Okay, consider other options. Okay. Any questions on this?
The undecided items is just going to be the difference between the best solution, right?
Well, we know the best solution, and we know the sum of the taken values. So what's the sum of values of the undecided items? How do we compute this? Well, we just sum them. So right, we are given an array, right? So what's the input to the knapsack problem? We have this array of weights, and there's an array of weights and an array of values. So we have value 1, value 2, value 3, value k plus 1, value k plus 2, value n. So what's k? Let's assume that k items have been decided here. K items decided. That we have decided k items, and n minus k items are yet to be decided. We decided k, and n minus k are yet to be decided. Now, if I compute the sum of values of these, I just sum these values. This is the input array. This is input to the, I know this. This is an input to the algorithm. I compute the sum of these values.
Are they sorted?
Doesn't matter.
Doesn't matter.
So does this require sorting?
No.
No. So just sum the values of these items and add them to the value of taken items. And this will give you an upper bound on the value of any solution below this node. Any questions? And now, in order to sum these items, how much computation? What's the asymptotic complexity for summing these items? Well, it's n minus k. So it's n minus k. So it's O of n minus k. Or in fact, it's exactly theta of n minus k to compute the sum of these items. But in fact, if we think about this carefully, we will be able to calculate the sum of undecided items with only O of 1 work at each node. So here, with what I have described so far, in order to compute the sum, I have an O of n algorithm, basically. This is an O of n algorithm to compute the sum of undecided items. Right? So can you think of an O of 1 algorithm for computing the sum of undecided items? Yeah.
Could you compute it the first time, the sum for the total, and then just pass that value down each time and subtract that item from it?
Yeah, okay. So that's a good start. That's a great start. We can, from the beginning, calculate the total sum. Calculate the total sum. Of course, how much computation will that cost us? Theta of n, which is nothing, right? Theta of n is nothing compared to this exponential search. So we can easily, spend that theta of n, and we have to do it only once. Only once in the very beginning. We calculate the total sum. So suppose that the total sum is 200. Then how do we calculate the sum of undecided items?
We need to have a track of the items taken and their value summed up.
Well, okay. So if I tell you that the total sum is 200, and the sum of, so let's write it here. Total sum equals 200. Sum of taken values equals 40. What does this tell us? Can we calculate the sum of undecided items? No. So if we subtract 40 from 200, what will this give us? Untaken items and undecided items. Because an item can be in one of three states, right? Taken, not taken, undecided. There are no other options. So each item will be taken, not taken, or undecided. So taken, not taken, this is the decided items at a given node. So this is our partial solution. So the missing piece of the puzzle is what? In order to calculate the sum of undecided items, what do we need to calculate as well?
We should have the count of undecided, not taken item value.
Yeah, exactly. The sum of untaken items. But this is something that we can easily do, right? We can track the sum of untaken items. Whenever we do a branch on a 0, whenever we do a 0, we just sum untaken items. We sum the sum of untaken items. In fact, we can do it here. We can track both taken and not taken. So let's do these numbers here. Initially, taken equals 0 and not taken equals 0, right? So when you go to this, taken equals 0 and not taken equals, we decided not to take item 1, so we already lost 10. So this is our loss, because we decided not to take item 1. Our loss is 10. And here when we decide not to take item 2, our taken equals 0 and our not taken equals 30. So this means that our loss is 30 so far. So sum of untaken values. If the sum of untaken values is, for example, 50, then what's the sum of undecided? What's the sum of undecided? 110?
Total sum minus 1.
Okay, so the sum of, yes, the sum of undecided is 110, yeah. Now what's the upper bound? Upper bound on best solution below the current node. What's our upper bound now? So the sum of undecided items is 110. So we have taken 40, and undecided is 150, 110. So basically our loss is 50. So we can just subtract 50 from 200, and this is our upper bound. So our upper bound is 200 minus 50. So here we can say, okay, our upper bound here equals the complete sum. Our upper bound is 60, right? Our upper bound here is 60. Our upper bound here is 50 because we have lost 10. Our upper bound here is 30 because we have already lost 30. We have decided not to take 30. So the best that we can do is 30. And this is an upper bound. It doesn't mean that we can actually get 30. Remember, it's an upper bound. Okay? So here, for example, the sum of taken items is equal to what? What's the sum of taken items at this node? 20. And the sum of not taken items or untaken items
10.
is going to be 10. So basically, whenever you do a 1, you add the value of the item to the set of taken. So you track taken value and untaken. So whenever you do a 1, when you take an item, you add the value of that item to the t. And whenever you decide not to take it, you add the value to the n. So now, what's my upper bound here at this node? The upper bound is 30. How much did I lose? I only lost 10, so my upper bound is 50. That's my upper bound. So I still have the hope to get 50. Now this upper bound, this is an upper bound, but in fact this is a loose upper bound. It's not a very tight upper bound. It's not a very precise upper bound. Now can you think of a way of making this upper bound tighter? So if I tell you that the sum of taken values is 50, the sum of undecided items, values of undecided items is 40, and you know the values and the weights of the undecided items. If you look at the values and the weights of the undecided items, will you be able to compute an upper bound that is better than 90? Based on what? So can you think of, it's like by doing this sum of values of undecided items, we're being very optimistic. We're assuming that we can take all the remaining items. This is too optimistic. Sometimes it may be clear that this optimistic assumption is not true. Yeah. Yeah, so if you look at the weights of these items, of these remaining items, if one of them already exceeds the remaining capacity, then it won't fit, and we don't include it in the sum. So if the sum of undecided items is 40, and say the remaining capacity what's the remaining capacity? What do we mean by the remaining capacity?
Total minus taken values.
Yeah, exactly. Well, the C minus sum of taken weights. Remaining capacity is C minus sum of taken weights. Okay. Okay. So if the remaining capacity, say, is 30, then any item with weight greater than 30 should not be counted. So if we put some numbers here, suppose that I have 4 items left with 10, 35, 30, and 5. If these are the weights of the remaining items, then I know that this will not fit. So I will not calculate this. So I will not include the value of this in my upper bound, and this will give me a better upper bound, closer to real. So we're looking for an upper bound that is as close as possible to the real value. Okay. So now in this case, if we are going to scan the items and determine for each item whether we should include it or not, depending on the remaining capacity, then we will have to spend O of n time. So it's with this description, we'll have to spend O of n time at each node to calculate the upper bound. Now remember, in this branch and bound, what we are trying to do with branch and bound is to compute a bound, hoping that the time that we invest in computing the bound is going to pay off by leading to some pruning. So obviously, if every O of n that we invest is going to lead to pruning a subtree, the subtree is exponential. The size of the subtree is exponential in an exponential function of the number of remaining items, which is n minus k. So this can be in general, this can be much larger. The number of tree nodes that we pruned can be much larger than the time that we spend computing the bound. So computing the bound is an investment, and we would like to compute the tightest possible bound, as long as it doesn't take too much time. If computing the bound takes too much time, then the benefit from computing a more precise upper bound may not lead to a net positive result. In other words, the time that we spend computing the bound may outweigh the benefit from the pruning. Right? So you invest some time in computing the bound, and you hope to compute the tightest and the most precise bound, because a tighter bound will lead to better pruning. Right? So a tighter upper bound here means a smaller number, and a smaller number will lead to pruning at a higher level in the tree. So you want your pruning to happen as early as possible. You know, when pruning happens early at one of the higher levels in the tree, then it will be more beneficial. It will save you a lot more computation. Okay, so if the sum of values of undecided items is 40, and say the sum of values of undecided items that fit in the remaining capacity equals, say, 25, then this is going to give you an upper bound of 75. In this case, your upper bound, it will give you a better upper bound of 75. Okay? And, 75 can be, for example, if the best solution was 85, if the best solution was 85 instead of 100, then this upper bound that sums all the values of the undecided items gives you a 90. With 90, you will not prune. But with 75, you will prune. Okay? Okay, so any questions? So now, is this the best upper bound that we can compute? The answer is no. In fact, there is a much better upper bound that we can compute for the 0-1 knapsack problem. And that upper bound is based on the fractional knapsack problem. So this is an idea that we use in BranchandBound, where we use the solution to a relaxed form of the problem, or a less constrained form of the problem, as an upper bound on the optimal solution for the more constrained form of the problem. Well, okay, so let me explain this. Now, which problem is more constrained, fractional or 0-1 knapsack? 0-1 knapsack is more constrained. Knapsack is more constrained. So any solution, any feasible solution to the 0-1 knapsack will have to satisfy the same constraints that a solution to the fractional knapsack problem satisfies, plus an additional constraint of integrality, of being, of taking only 0% or 100% of each item. So with the 0-1 knapsack, you can only take 0% or 100% of an item. With the fractional knapsack, you can take any fraction you want, anything between 0 and 100%. So this is more constrained. Now, if you compute a solution, if you are given a 0-1 knapsack problem, and you ignore or relax the constraint of integrality, that the items can be taken or not taken, or assume that you can take a fraction, this will give you some solution. That solution will be an upper bound on the optimal solution for the 0-1 knapsack. So if we look at this specific problem, if we look at the big problem, Now, if we were to solve this as a fractional knapsack, what will we get? So if we solve this as a fractional knapsack, so for item 1, the value per unit weight is 10 over 2. So this is 5. And this is 20 divided by 5. This is 4. And 30 divided by 9 is 3 point something, 0.1. 30 divided by, well, 3.3. 3.3. 3 and a third. OK. So the fractional solution, see, we're not changing the problem. We're still doing 0, 1 knapsack, but we're using the fractional solution as an upper bound. So if we solve this as a fractional problem, we will take item 1 completely, item 1 completely, and item 2 completely. Item 1 will give us a value of 10. Item 2 will give us a value of 20. And then how much space do we have left? So the sum of these is 7. 7 subtracted from 12 is 5. So we can take 5 kilograms of the least valuable item, which is item 3. Right? Now 5 kilograms of items 3 is going to be 5 over 9 multiplied by 30. So this is what? This is about half. So it's about 16 or something. It doesn't matter. How much is it? Yeah, so it's slightly better, more than half. But
16.5.
16. So this is 30 and 16. So this is what? This is 46. So the fractional solution is 46. Now what's the actual solution for the 0, 1 knapsack? It's 40. So this will always be the case. The optimal solution to the 0, 1 knapsack problem will be less than or equal to the optimal solution to the corresponding fractional problem, or to the problem, to the fractional problem, or to solving the same problem pretending that it's fractional, or ignoring the integrality constraint. Okay? So by ignoring that constraint, when you ignore a constraint, you will get something bigger. Right? So that's why this is an upper bound. So an optimal solution, or an upper bound on the optimal solution to a given instance of the 0, 1 knapsack problem can be computed by finding an optimal solution or by solving the problem as a fractional knapsack problem. By solving the problem as if it were a fractional knapsack problem. Okay. So is everyone convinced that if you solve the problem as if it were a fractional knapsack problem, you'll get something bigger, or you will get an upper bound? It could be equal, by the way. It's not necessarily bigger. but it's an upper bound. Why? Because any solution, so if this is the optimal solution to the fractional problem, any solution to the 0, 1 knapsack problem must satisfy the constraint of the fractional. Any solution to the 0, 1 knapsack must satisfy the constraints of the fractional. But the opposite is not true. So any solution to the 0, 1 version of the problem is a valid solution, for the fractional. It's not necessarily optimal. Any solution for the 0, 1 knapsack problem is a valid or is a feasible solution for the fractional. And by definition, the optimal solution to the fractional has a value that is greater than or equal to the value of the solution for any valid solution for the fractional. Okay? Now, how can we use this in pruning? How can we use this idea to do pruning? So we're looking for an upper bound, right?
And we use it against undecided items?
Yeah, exactly. So with undecided items, so you have these items decided, and you have undecided items. So just take these undecided items and solve the remaining problem as a fractional knapsack. Pretend that it's fractional. And of course, what will your capacity be here?
Remaining capacity.
The remaining capacity, yeah. So take the remaining capacity, which is the capacity minus the sum of weights of taken items. You get the remaining capacity and the remaining items. So this remaining subproblem solve the remaining subproblem as if it were a fractional knapsack problem. Okay? Solve it as if it were fractional, and this will give you a value. So if it gives you, for example, 70, solving this as a fractional problem gives you 70, then you know that this is an upper bound. You know that the actual optimal solution for these remaining items is something less than or equal 70. So you know that the actual is going to be less than or equal 70. And 70 is an upper bound. Okay? Questions? In fact, you will implement this. You will be implementing this, and you will see how much difference this will make. So, we were talking about numbers. 2 power 50 is going to be hopeless with brute force. But when you apply these upper bounds, you may solve 2 power 50 or size 50. You'll solve it in seconds or maybe fractions of a second, depending on your upper bounds and your implementation. So, and 2 power 100, you can solve 100, right? Brute force for 100 is billions of years. But with upper bounds like this, you can solve it within seconds or a fraction of a second if you compute bounds, because these bounds are going to help you prune exponential subtrees, subtrees with exponential sizes. So you will be doing very substantial pruning that will allow you to solve fairly large problems within seconds. Okay, so now let's talk about, are there any questions? So let's talk about the implementation. By the way, this is something that we can generalize. So generally speaking, to compute an upper bound on a sum optimization problem, you can find a relaxed version of the problem, a less constrained version of the problem, and you solve it optimally. So the optimal solution to the less constrained form of a problem is an upper bound on the optimal solution to the original problem. So an optimal solution to a less constrained or relaxed. Fractional knapsack is a relaxation of 0-1 knapsack. To a less constrained or relaxed version of a maximization problem is an upper bound on the optimal solution to the more constrained problem. Okay, so let's now write the code for this. Well, the code is going to be, let's do just DFS traversal. And DFS traversal for the tree, we can do it with recursion. So we can, all what we need to do is something like find, well, the initial call is going to say, OK, find solutions. Well, we'll need a find solutions recursive function that takes I, where I is the level, or I is number of item to decide. So find solutions of I. All what you need to do is don't take I and then find solutions of I plus 1. Then take, let me put it low because we'll need more code. OK, don't take I, find solutions of I plus 1, take I, find solutions of I plus 1. So what does this mean? It means that don't take I, you decide not to take I. OK. Now you decide not to take I. Then now you have a new root. So you repeat the same thing from this new root. So this is the recursion. Find solutions. So explore the subtree below this entire subtree. Then after exploring the entire subtree below, don't take I. You try to take I. And then you explore the subtree below it. OK? So make a decision. Recursively explore the subtree below this. Make another decision and explore the subtree. Now, let's assume that we will keep our solution in an array. So we will have two arrays. That will hold the solution. So the solution is going to be a Boolean, an array of Booleans that indicates for each item whether it's taken or not taken. Right? So you have n items, an array of size n that will indicate for each item taken or not taken. That's your solution. But why do we need two arrays for the solution?
For the decided ones and undecided ones.
No. Well, the array will have decided and undecided. But in order for this to work, why do we need to keep two arrays? So when you are trying to find the maximum number in an array of integers, you will need two variables, right? One variable for the current item and one variable to track the max. So you need an array to keep the maximum value, the best solution found so far, and an array for the current solution. You need two arrays. So two arrays, A current and A best. Of size n. And assume each array has the following attributes. A dot taken, which is sum of taken values. A dot untaken, sum of untaken. Why do we need untaken values? So that we can compute the upper bound by subtracting from the total sum. And A dot taken weight, sorry. So this is taken weight. So taken value, sorry. So we need both, taken value, untaken value, sum of untaken values, and taken weight, sum of taken weights. Now, so now this take, so let's say this take function, take of I, what is it going to do? Take item I, so what it's going to do is A current dot taken value plus equals the value of item I, and A current dot taken weight plus equals the weight of item I, and it's going to set A of I to what? To true. So when you step forward by taking an item, you set A of I for that item to true, and you add the value of that to the sum of taken values, and you add the weight of that item to the sum of taken weights. And similarly, don't take, yeah, so this is maybe a little bit, it's not visible, so we'll, okay, so now it's there. So don't take I is A current dot untaken value plus equals the value of I, and A of I equals what? False. So this is take and not take. Now what is missing here? The base. So where is the base here? When we reach a leaf, right? When we reach a leaf, the base is when we have a complete solution and we want to check it. So we want to check it for feasibility. So what will be the value of I when we reach the base?
Input level.
So remember, at this level here, when we are trying to decide this, here I equals 1, I equals 2, I equals 3. So when I equals n, we're still trying to decide the nth item. When I equals n plus 1, we have already decided all items and we have a complete solution. So in fact, the base case is I equals n plus 1. Because when I equals n, we're still trying to decide n, take and not take, and try to decide what to do with n. So in fact, if I equals n plus 1, then what we will do is to check feasibility. And checking feasibility is a current dot what? Dot taken weight. Oh, so we need an if statement. If a current dot taken weight is less than or equal to what? The capacity, the complete capacity, then this is feasible. And if it's feasible, what should we compare?
Best solution.
With the best solution. Yeah, we should compare current with best. So if the current solution is feasible, if a current dot taken value or weight value is greater than what? A best dot taken value. So this means that, is it feasible? If it's feasible, then if its value is greater than the best value, now it becomes the best. So now we say, okay, copy, or let's assume that we have this a best equals a current. So now the best becomes the current. Okay. Now there is a bug in the code. So there is something important missing. What is missing here? This code, if you run this code, it's going to crash. And
Base condition.
So this is the base case. Decide, find solutions, take. Sorry, don't take, find solutions, take, find solutions. What are we missing here?
Return.
So we need to return, right? If you are doing the base, after you handle the base case, you need to return. Otherwise, you will be executing these with I equals n plus 1, and it will crash. So at what level should I put the return? Should I put it under this if? Under which if? So there are 3 ifs. Under which if should I put the return? Yeah, exactly. Under this if. So the return should be at this level. Because for the base case, whether it's feasible or infeasible, whether it's better than the best solution or not, I must return. Okay, so then I return. Well, I assume that a current and a best are global arrays that are stored there. By the way, when you write the assignment, you will have to deal with all of these details. Okay, so now this is the brute force. The code here is the brute force. Okay, but in fact, there is something here missing. So now, when I do make a decision like take or don't take, and then after I'm done with this decision, after I explore, so for example, this decision, I decide to take item 1. Then after I explore the subtree, or let's look at this decision. I decide to take item 2. And after I explore the subtree below it, I need to return, right? So after I explore this subtree, I need to return. So I need to undo whatever I did along this branch. So when I decided to take an item, I did this work. I updated, taken V and taken W. So after I'm done with this, I need to undo this. So I need a function undo take. Find solutions, undo take of I. So undo take of I is going to do a current dot taken V minus equals V of I, and a current dot taken W minus equals W of I. And do I need to undo this? So, I stepped forward by exploring this. When I return, no, in fact, this will get overwritten. I can do it for completeness, but it's not necessary because it will get overwritten, because there will be another decision. For example, if I make this decision here, and then I backtrack, and then I go here, when I make this decision, I will overwrite the entry for element 2 with a 0. So I'm here. I made this decision. I returned to this. I returned to the root. Then I did this. Now when I do this, this is going to overwrite this. Right? It will overwrite it. So I don't need to do a of I equals false or a of I. Well, in fact, I don't need to do it. So what should I set this to? OK. And I need an undo untake of I, and undo untake of I, or undo don't take of I, and that's going to be a current dot untaken V minus equals V of I. So I need to do untake of I. Now, do I need to do undo don't take? Well, for the brute force, do I need to do undo don't take? Don't take is going to update the untaken value. I'm not using it yet. So we'll use it when we compute the upper bound. So for now, well, we can do it for completeness, in fact. We can do just find solutions, undo, don't take of I or I plus 1 I. OK? So now this is the brute force. To implement the backtracking, what do I need to do? One line or two lines? To implement backtracking. What's backtracking? No, backtracking doesn't involve any upper bound. What's backtracking? So we check only for feasibility. We check the sum of taken weights. So all what I need to do is this. For backtracking, if a current dot what? Taken W or V? Taken W is greater than C, return. This is backtracking. This line does backtracking. So with brute force, you only check when I becomes n plus 1. But with backtracking, you always check the sum of weights of taken items. If the sum of weights of taken items exceeds the capacity, then you return. So this is backtracking. Now, how do I implement the first upper bound that we described? The upper bound, which is just calculate the sum of undecided items and add it to the sum of taken values. So let's try to write it here. If, what's the sum of taken values? Sum of taken values, well, we can say if total sum of values minus what? The total sum, we need to subtract the sum of the sum of untaken, which is A current dot untaken value. A current dot untaken value. This is our upper bound, the total sum minus the sum of untaken. Remember the loss. This is our loss. This is the total sum of values. The total sum is piece of cake. We can calculate this in the beginning just by summing the values of all items. And if this is what, we compare this with what? So this should be compared with the value of the best solution. If this is less than or equal to A best dot value, if it's less than or equal to the best value, then I return. Okay? So everything in black is brute force. The blue here is backtracking, and the blue here is branch and bound with the simple upper bound. The simple upper bound is you take the total sum of values, and what's our current loss? Our current loss is the items that we have already decided not to take. All other items, whether they have been taken or undecided, we count them as taken. That's our upper bound. So this is the upper bound. This thing is our upper bound. If our upper bound is less than or equal to the value of the best solution, then we will not be able to beat the best solution. If we cannot beat the value of the best solution, we will return. Okay?